This week, we're going to go into more detail about quantum query complexity. Last time we talked about Grover's algorithm, which can solve a general search problem. And to motivate studying search problems, we gave as an example the problem of finding a satisfying assignment to a formula. And so here, again, I have an example of a formula in conjunctive normal form. So we have these clauses, which is the or of three literals, and then we look at the and of those clauses. And so this is known as the three-sat problem, the problem of finding a satisfying assignment to a formula of this form. And we don't actually think that quantum computers can solve this problem efficiently, right? This three-sat problem is an NP-complete problem, and we don't believe that there's a polynomial time algorithm to solve this problem. And part of the reason why we think that comes from this model of quantum query complexity. Okay, so in this lecture, I'm going to introduce more about quantum query complexity and talk about how we can actually show lower bounds on quantum algorithms in this model of query complexity. And so we can actually show some limitations of quantum computers. We can get some idea of what problems we think that quantum computers cannot solve efficiently. So we've already seen the query complexity model quite a bit. So a lot of the algorithms that we've been talking about, we've already discussed them in the query complexity model. So in the query complexity model, instead of being explicitly given an input, you can only access the input by making queries. So you have an oracle which gives you access to information about the input. And the question is how many times you need to query that oracle in order to find some property of the input. And the distinguishing feature of the query complexity model is you only care about the number of times you query the algorithm. Okay, so in between queries, you can take as much time as you like to think about what you want to query next. There's no bound on the complexity, on the time complexity or memory complexity of the algorithm. The only thing we care about is how many times the oracle needs to be queried. So even when you design algorithms in the query model, a lot of times the algorithms turn out to be time efficient anyway. So we kind of saw an example of this with Shor's factoring algorithm. So the quantum heart of Shor's factoring algorithm is this algorithm for solving the period finding problem. And we studied the period finding problem purely in the query model, right? So we assumed that we had oracle access to a periodic function, and then we queried that function in order to find the period, okay? But in the application of the period finding problem to integer factorization, the function that we wanted to find the period of, right? This function here, where f of a is equal to x to the power a modulo n, that function actually can be efficiently implemented with a small circuit. Okay, so then just plugging in that efficient circuit for the oracle actually gave us an efficient algorithm overall. Okay, because the other main operations that we were doing was the quantum Fourier transform, and we already saw that that can be done efficiently by a quantum circuit. Another motivation for query complexity, as I mentioned, is that we're able to show lower bounds in the query complexity model. Whereas, on showing lower bounds for time complexity or circuit complexity is a very, very hard problem. And we don't have large lower bounds in those models for explicit functions, either in the classical case or the quantum case. Okay, so this ability to show lower bounds on query complexity, it actually lets us show rigorous separations between the classical and quantum query complexity of certain problems. Okay, because in the query model, we can show classical query lower bounds, and we can give quantum query algorithms and thus give examples of problems that quantum computers can solve more efficiently than classical computers in this query model. Okay, and also, as I mentioned, we can show lower bounds on quantum query complexity, so that also shows us what problems are probably hard to solve even with quantum computers. Okay, now let's go into more specifics into how the query model is defined. And I'm actually going to start off with the classical case. Okay, so in the query model, there's some function that we want to compute. And I'm going to call this function f. So there's some function f that we want to compute. And this function f is known to everyone. So everyone knows that this is the problem that we're trying to solve. Now, what is unknown is an input x. Okay, so an n-bit string. So this is unknown to us, and we only have access to x via an oracle. Okay, and our goal is to compute f of x. Okay, and what this oracle for x does is we can ask questions like, what is the third bit of x? And the oracle tells us the third bit of x is 0. And then we can ask, what is the seventh bit of x? And the seventh bit of x, the oracle says, is 1. And we keep asking questions of this form until we have enough information that we can actually output f of x. Okay? And the question is exactly how many queries are needed in order to determine f of x. Okay? And I should just mention that the notation here is a little bit different than what we've been using, like when we talked about the Deutsch-Jozsa problem or Simon's problem. In those cases, we actually referred to the input as a function f, right? So the input was a function f, and in the case of Deutsch-Jozsa, we wanted to determine if that function was balanced or constant. Okay, so now when we're talking about query complexity, I'm going to kind of switch notation, and I'm always going to use x for the input. So the input is just going to be an n-bit string, and what we want to compute is determined by this function f, which maps n-bit strings to 0 or 1. And so on input x, we want to output f of x. Okay, so so that's a difference with the notation that we had before. So I hope that that's not confusing. And in the query model, we're usually interested in the worst case x. Okay, so we're interested in how many queries are needed to determine f of x for the worst case x, so for the x which requires the most number of queries. That's usually what we're going to be interested in, worst case complexity here. Let us begin with the case of classical deterministic query complexity. This model is very elegant because an algorithm is just described by a binary tree. In every node of the tree, we ask for the value of some bit of the input. We ask what is x1, for example. Now the answer to that is just going to be 0 or 1. So then our tree can branch on that answer and then decide to ask what another bit of the input is. So for example, if the answer is 0 to the value of x1, then we can ask the value of x2. And if the answer is 1, then we could ask something different, like the value of x3. Okay? Now in this case, this is actually a deterministic query algorithm computing the majority function on 3 bits. So in this case, we have a function majority on 3 bits. So we're going to have a 3-bit input and 1 bit of output. And majority of 3 on an input x is going to evaluate to 1 if and only if x has at least 2 ones. Okay, so if and only if a majority of the bits of x are 1. Okay, so this is going to evaluate to 1 if and only if the number of 1s in x, the Hamming weight of x, is at least 2. Okay, and I claim that this tree computes this function. Okay, let's see why that is. So for example, if we find out that x1 is 1 and x3 is 1, then we know that a majority of the bits must be 1 because we've already found 2 1s. Okay, so in that case we can just output 1. However, if x1 is 1 and x3 is 0, then we still don't know whether a majority of the 1s in x are 1, a majority of the bits of x are 1 or not. So then we have to ask another question, what is x2? And the answer to that tells us whether a majority of the bits of x are set to 1 or not. Okay, so you can check out all these paths and see that this tree does indeed compute this function, majority of 3. Okay, and the complexity of this algorithm is just the depth of this tree. Okay, so in this case, the depth of this tree is 3. Okay, so the longest length of a path from the root to a leaf is 3. Okay, and that corresponds to the number of queries that you make on the worst case input x. Okay, so that is our measure of complexity of a deterministic query algorithm, right? How many queries you make on the worst case x. So in this case, the query complexity of this algorithm is 3. So that's the case of deterministic algorithms. We can also consider randomized, classical randomized query algorithms. And a randomized algorithm is simply a probability distribution over decision trees. Okay, so basically at the very beginning of the algorithm, you make a random choice that selects a deterministic decision tree, and then you execute that deterministic decision tree. Okay, and that is a randomized query algorithm. Okay, so in this case, the output of the algorithm is a random variable, right? Because it depends on this random choice of which deterministic algorithm you execute. So the cost of an algorithm on input x is the expected number of queries made on input x, right? Again, this is expectation over the choice of the deterministic query algorithm that is executed. In the randomized case, there's different notions of what it means to compute a function. So there are zero error algorithms. These are algorithms that never make a mistake. So therefore, every decision tree in the support of the algorithm, of the randomized algorithm, has to compute f. Okay, but probably more common, and what we'll talk about more in this course, is the bounded error notion of computing a function. And in that case, we just have to have the probability that the algorithm on input x outputs the right value, f of x, is at least 9/10. Okay, and this has to hold for every input x. Okay, so again, this probability is over the choice of the deterministic algorithm that is run by the randomized algorithm. So this is not a probability over inputs. We want this to hold for every single input x. To see an example of a randomized algorithm, randomized query algorithm, let's go back to this majority function on 3 bits. And here's actually a zero error randomized algorithm. Okay, so we just randomly choose 2 positions of the input and query them. Okay, if they're the same value, then we just output that value, right? So if we see 2 1s, then we know the majority of the bits of the input are 1. So we know we can output 1. And likewise, if we see 2 0s, then the majority of the bits of the input cannot be 1. So then we can output 0. Otherwise, if we see a 0 and a 1, then we don't have enough information yet to determine the answer. So in that case, we query the 3rd bit and output it. Okay, so let's consider the cost of this algorithm. So let's think about the cost on a particular input. So let's say on the input 110, okay? So now with probability 1/3, when we randomly choose two positions of the input, then we'll choose positions 1 and 2. Okay, and so in that case, we see two ones and we know the answer. We know that a majority of the input bits are set to 1. So then we can just output 1. Okay, so with probability 1/3, we just have to make two queries. In the other cases, so with probability 2/3, we're going to see a 1 and a 0. So in that case, we don't have enough information to determine whether a majority of the bits are 1. So then in that case, we have to make a third query. Okay, so the expected cost of this algorithm on the input 110 is, with probability 1/3, we make two queries. So that's this factor of 2/3 here. And with probability 2/3, we make three queries. So that's this term of 2 here. Okay, so the expected cost of the algorithm on this input is 2 and 2/3. Okay, so it's less than we saw in the deterministic case, so where we had to make three queries. Okay, I showed you an algorithm that made three queries, but that's actually the best you can do. You have to make three queries for a majority of 3 with the deterministic algorithm. Okay, so we've seen the cost on one particular input, but by symmetry, this is actually the worst case. So in fact, this algorithm for every input x can compute majority of 3 of x with expected cost at most 2 and 2/3. So now we're in a position to define the query complexity of a randomized algorithm. And that is just the minimum over all possible algorithms of the maximum over the inputs x of the cost of the algorithm on x. Okay, so it's a worst case notion of cost, right? So that's corresponds to this maximum over all inputs here. And then we minimize over all possible algorithms that compute f under the notion of error that we're interested in. Okay, so we define R0 to be the minimum over all zero error algorithms, and for the bounded error algorithms, we just minimize over algorithms that are correct on every input x with probability at least 9/10, and we call that R of f. Okay, so these are the definitions of the randomized query complexity. Now let's consider the quantum model. Okay, so we've already dealt some with quantum query algorithms, so I'll just review the setup here. So we try to make the quantum oracle as analogous as possible to the classical case. Okay, so our oracle on input x is going to behave as follows. So we have a state here with two registers. So I here indicates the position of the input that you want to query. B is just a bit, basically determines if the oracle is, going to take an action or not. And so the oracle for input x on this ket I, ket b, if b is set to 1 and xi is set to 1, then it's going to multiply the phase by -1. Okay, and otherwise it's going to do nothing. So you see that when b is equal to 0, then the oracle always acts as the identity. It just doesn't do anything. And we call this a null query. Okay, so it's a little bit wasteful, to have the possibility of a null query, for every single value of I here. So what I'm actually going to do is to use a more compact notion of the oracle. And again, we think about the positions in our input x, so the indices into input x, as they can take the value from 1 to n. Okay, so we use one indexing into the positions of x. And so in this more succinct oracle, I just have one register, but I let I now take on values from 0 to n. Okay, and when I is 0, I just consider this as the case of the null query. Okay, so if I is 0, then my oracle just acts as the identity, and otherwise it flips the sign of the phase depending on whether or not xi is set to 1. Okay, so this is kind of a more convenient oracle. We just have one register, and that's what I'm going to use from now on. And usually I won't write the tilde. Okay, so I'll just consider this action of the oracle to be OX. Okay, so now is a good time to pause and just think about, why do we need the null query at all? Okay, so think about that for a second. So to see why we need a null query at all, let's just think about the case where our input is just 1 bit. Okay, so X is just 1 bit, either 0 or 1. Okay, and suppose that we didn't have a null query. Okay, so then our register could only hold the value 1, right? Because X only has 1 bit. And what's the action of the oracle when the input is 0? Well, this is always just going to return 1 again. Okay, and the action of the oracle when the input is 1, well, that's going to flip the phase. Okay, but you see now these two states, they just differ by a global phase. Okay, so we have no measurement that is able to distinguish these two states. Okay, so if we didn't have a null query, then we basically cannot tell if X, the input X, is just 0 or just 1. Okay, so on the other hand, when I have a null query, okay, so now my register has two possible values. It can be 0 or 1. Okay, so I will just drop normalization here. Now when we act, when the input X is 0, so this again is just going to act as the identity. But when the input is 1, okay, then something different happens now. Okay, so the 0 state is just mapped to the 0 state. That's the null query. But now on the 1 state, then we're going to flip the phase. Okay, and now these two states are orthogonal. Okay, so now we can distinguish these two states by a measurement. Okay, so that's why we need the null query. Now we've discussed the action of the oracle in the quantum model. So in addition to the query register, we also allow the algorithm to have a workspace register. So this is basically an arbitrary register. You can take as much memory as you want. So let's just say it's m qubit register. And so our algorithm, these are going to be the basis states for our algorithm. Okay, so these two registers, you have your query register and your workspace register. And we always assume that the algorithm begins in the state where everything is initialized to 0. Okay, so both the query register and the workspace register is just initialized to the all 0 string. Okay, so what happens in a quantum query algorithm? So the algorithm begins in this all 0 state, and then we alternately apply the oracle and an arbitrary unitary. Okay, so remember that in the query model, we don't care about the complexity of operations. So you can actually apply any unitary you want. It doesn't have to be, have a small circuit or something. You can just apply any unitary you want. Okay, so a T query algorithm is determined by these unitaries that you apply, U0 through UT. And at the end of the algorithm, then you're going to do a two-outcome projective measurement, let's say with projectors pi 0 and pi 1. Okay? So on input X, after you've made little t queries, the state of the algorithm is the following. So again, we start out in the all 0 state. Okay, and then we can apply a unitary, we apply the oracle, we apply another unitary, etc. Okay, so this is the state of the algorithm on input X after little t many queries. So again, here's the state of the algorithm after little t many queries. And if the total number of queries made is capital T, then after we've made capital T many queries, then we're going to apply our measurement. And the probability that the algorithm outputs 1 is just going to be the norm squared of pi1 on the state of the algorithm, after capital T many queries. So pi1 on psi xt. And we say that the algorithm computes f with bounded error if and only if for every x such that f of x equals 1, then the norm squared of pi1 on psi xt is at least 3/4. Okay, and for every x such that f of x is equal to 0, so the same norm squared is at most 1/4. Okay, so this is the definition of a t-query algorithm computing f with bounded error. So as in the previous cases, the quantum query complexity of a function is the minimum number of queries made by a quantum algorithm that computes f with bounded error. Okay, so again, we're going to minimize over all possible quantum algorithms that successfully compute f in this sense with bounded error. And that's the definition of quantum query complexity.